we're going to spend a few minutes talking about rationalizing denominators. This is just a way of rewriting expressions so that you don't have a radical in the denominator. That's all that it really means. Okay. So for example, if I take this guy right here, 1 over the square root of 3, I want to be able to rewrite this fraction so that I don't have a radical in the denominator. Now I know for some of you, you're like, oh, that's no problem, Mr. Craig, I just wouldn't even write the radical sign to begin with. But that's not really valid. What do you think we can do here? What do you think is a valid thing that we can do with fractions?
The time to divide radical into 3.
Reciprocated.
No, I can't just do the reciprocal of something. I have to do something where it doesn't change its real meaning. And that's when we can multiply times a form of 1, right?
Which is a reciprocal of 3 over 3.
If I do 3 over 3, that doesn't help me out. But what if I did the square root of 3 over the square root of 3? What if I did
That's what I
that?
meant.
Now, if you look at this, isn't the stuff that I have here in magenta, I'm not going to call it pink, isn't this 1? Doesn't that really equal 1?
Yes.
Now, why is this useful? Why did I pick the square root of 3 as opposed to something else?
It's had the same radicand.
Well, it's not really about being the same radicand, although for some examples that is true. But what happens when I multiply these radicands or these radicals together in the denominator? What do you get?
6. Oh, 3 times 3 does 9.
Is
Sorry.
9, right? And what's great about the square root of 9?
It's 3.
It's 3 without a radical, right? So that means I've turned my denominator into something that's not a radical, but an integer. But in the numerator, I do have the square root of 3. That guy can't go away. So when I finish this, I have the square root of 3 in the numerator over 3. And you may say, well, what's the purpose of me rewriting this so I don't have a radical in the denominator? Well, some textbooks don't even care if there's a radical in the denominator. Others do. They get very adamant about it. But a great thing about this is that you could rewrite this, not that you have to, but this really means 1/3 square roots of 3. So you can see that more as a coefficient, and that would allow you to add this guy to other square roots of 3. So we're able to rewrite this in a way where you can combine it with other like radicals. Okay. If it was in the denominator, you couldn't really do it too well.
How do you get the whole number of 3 then?
What's the square root of 9? Yep. So I multiplied this so that I could create a perfect square in the radical, so that when I simplified it, I don't have a radical in the denominator. Let's see if we can take the same concept and apply it to a different problem. Let's do 4 divided by the square root of 7. How could you create a perfect square for the radicand that's in the denominator? We could use the square root of 7 over the square root of 7. What would you get in the numerator?
4.
You get 4 square roots of 7. 4 is outside the radical, 7 is inside, so they're not allowed to multiply. What do you get in the denominator? Right, and this is where you could almost this is where you could almost just take this guy as a little side note and say, I know this is the square root of 49, and that's just going to equal 7, so that way I don't have to keep rewriting a bunch of stuff. So it's 4 square roots of 7 over 7.
And then when you're saying the square of a square is itself, so the square of a square is itself.
The square of a, that's not what you mean. You mean the square root of a square. You said the square of a square, and don't even say that's the same thing. The square of a square is actually something to the 4th power.
No, you just said.
And you said the reason why you can't multiply the tops is because they're not like
Well, no. The reason you don't you did multiply these to get 4 square roots of 7, but you can't do 4 times 7 because one is outside the radical, one is inside the radical. Those guys don't go together.
Oh yeah, when we were just finishing the difference of squares, and we squared a square.
No, I squared a square root. I squared a square root.
Squared a square root, which
Yes.
is itself.
Which just gave you the radicand.
Well,
Yeah.
we just gave you the number what's in the, yeah.
Yep.
So that's what that is though, right?
Yeah, essentially. But it's not always going to be that way though. Did you say yeah right or yeah you're right?
I said, never mind.
Because I know I'm right. I just want to hear it from you, and I want it to be recorded. That'd be awesome. That we could go back and play it and do a little subliminal messaging while you sleep. You're right, Mr. Craig. You're right. It's cool. Hey, are you using swear words under your breath? I saw that. 6 over the square root of 2. How can I simplify this guy? What do you think you're going to use here?
2 times 2.
The square root of 2 on the top and bottom? Okay, so what do you get in the numerator?
That's to get a common denominator, right?
No.
No?
Square root of 2 over 2. It's over 2.
You get 6 square roots of 2. In this denominator, what's going to happen?
It's
It's going to multiply to give you.
It would be a 4 inside the square root, but that just gives you...
2. See, that's
Two.
what I mean.
And then we divide.
Am I done?
No.
No, I'm not, because there's simplifying that can be done.
2.
Now, don't give me this look like you're upset with me. I mean, you may be, and you can roll your eyes all you want to.
I'm hiding it pretty good, trust me.
If I had this written as 6x over 2, how would you reduce that?
You would divide the 6 by the 2.
It's
You would get
3x.
You would reduce that, and you would just get 3x, right? That's essentially what I'm doing here. This 6 and the 2 can reduce because they're just numbers out here, and they're common factors, a common factor of 2, and you have 3 square roots of 2. So I went from having an expression with a denominator with a radical to one that doesn't have a radical in its denominator. And the way I did that is that I multiplied times the square root of 2. And, this may help you out if we do this. Okay? Inside my radical, I have a factor of 2. But I want to create something that's a perfect square so that it completely simplifies out of the radical. Well, what factor would be missing to complete this guy so that he is a perfect square? He's missing a factor of 2, and that's what I put here in magenta. Okay? So if I put it here in the denominator, that would change my problem, unless I also adjust the numerator by the same factor.
What's magenta mean?
It's pink.
Huh?
It's pink.
It's a
I don't want to say
purplish-
I don't want to say pink.
It's a purplish pink.
It's pink.
I'm way
A silvery.
Mr. Craig needs words.
I'm trying to learn new words.
No, you don't want to sound unmanly. Mr. Craig is 42. We've been trying to figure out his age since last class.
Well, he just said he graduated tonight.
Wait, what happened?
Wow. You don't look it. You look 39.
If I have 3 over the square root of 8, if I have 3 over the square root of 8, what are you going to do here?
You can multiply.
Just be 8.
What do you mean, just be 8?
You can multiply by
You got
the square root of eight.
That is not good.
Square root.
So I'm going to multiply top and bottom times the square root of 8. So what do you get in the numerator?
8.
3 to the square root of 8.
3 square roots of 8 over what?
8.
Over
The
here.
number
Got a lot of
8.
use prepositional phrases when you're saying that, right?
It's not appropriate. Although we did say over 8. So that would be a prepositional phrase. Anyway, I'm not done here though.
Well,
Because why? How? What am I going to simplify?
that's 8.
I can just cross out these 8s, right?
No.
No.
It's 4 and 2. And then
I can break this deck. See, I can't reduce the 8 and the 8 because they're not common factors, because this guy's inside the radical and that one's not. But I can break this down to be 4 times 2, right? So 4 is a perfect square, and it's the square of 2. So what do you get in the numerator?
Square roots of 2.
You get 6 square roots of 2 over 8.
Now you're gonna
And you know what? If it makes you feel better, just pretend you didn't have that denominator. How would you break down 3 square roots of 8? Bless you. You break down the 8 with 4 and 2. And this 2 comes out times the 3 is 6. I still have to finish simplifying this. What do you get?
You have to divide by 2.
Common factor of 2, so you get 3 square roots of 2 over what?
4.
Well, that's a lot of work, right?
Yes.
Because this is not the way I would have done
That's what you just did.
it. No, I asked you what you would do, and you guys said I would use this. You said use the square root of 8. I said, all right, fine, let's do that. Now, let me show you how I would do this. If I look at 8, isn't 8 made up of 2 times 2 times 2? Right? So I'm dealing with the square root, which means I need to have perfect squares, which means I need 2 of the same factor. Well, I've got 2 times 2 times 2, right? So that means when I look at this by itself, isn't that already a perfect square? So what factor is missing to complete this being a perfect square?
2.
Just 1 2, right? So if I multiply top and bottom times the square root of 2, okay, that means in the numerator I get 3 square roots of 2. What happens when I multiply these square roots in the denominator? What do you have?
16.
The square root of 16, and what's the square root of 16?
4.
Oh, no.
When you do the second one, you can read.
Do you need to multiply 8 times 8 to create a perfect square? No. If you just multiply 8 times 2, you get 16, which is a perfect square. So using 8 wasn't wrong, it just creates more simplifying work for you at the end. That's the only difference here.
That was all.
Okay. What I like to do is I like to think about what factors do I have in my radical. I'm dealing with the square root, so I need perfect squares. So things have to pair up. Little buddy system here. So 2 and 2, but then there's this oddball factor of 2. He needs a buddy. His missing buddy is just one factor of 2 that I put in the numerator and denominator.